Okay. So yeah, thanks a lot, Scott and Hojae, for volunteering to present today on such short notice. So yeah, the two of them have been going into the literature for the past days, kind of looking at what are other approaches people have been taking for this kind of object and pose recognition task that Monty is currently doing, so that we have some kind of baselines that we compare to when we write up a paper about Monty's capabilities. So we can talk about that now, and then if that doesn't take up the whole time, there are also a bunch of questions people have been sending in that we can talk about more, or we can do that next week. Yeah, then I'll give it over to you two.
Sounds good. Okay. So yeah, we'll put together some slides for that will primarily go into some state-of-the-art methods for pose estimation, and I'll get to why we're kind of focusing on this first. So about a week ago, Scott, me, Vivian, and Nils had like a research kind of brainstorming meeting on how to demonstrate Monty capabilities for a paper that we can write up by the end of the year. So some of the starting point was kind of these kind of broad objectives, like demonstrate rapid learning for computer vision, whether that be from number of images or total data that's being used by Monty, rapid inference with multiple sensors, improved/robust recognition, and multimodal transfer. We came up with additional things that we may be able to show, but I don't think these are current or not fully implemented in Monty yet, but some other ideas that were suggested were generative or predictive reconstruction of input. So if we're seeing part of an object, if Monty can kind of reconstruct the rest, and continual learning.
Can I just make a comment on that? I think predicting the rest is the right thing to do. Reconstructing doesn't seem right to me. There's no place in the brain where images are reconstructed. You know, we're not good at that, but we are good at predicting what will be someplace and then seeing that. So as long as it's, I mean, I don't think our system's going to be good at generative models. Humans aren't good at that. So I think the predictive ability of Monty should be really good.
Gotcha.
Yeah, that's what I said too. And I think, like you said, it should be really good at predicting, using its models to predict. But if it's supposed to be like photorealistic generation, for example, we would need to train some kind of decoder on top of that, which might actually also be pretty good because it gets better information to use for this kind of photorealistic reconstruction. So it wouldn't be too difficult, I think, to add as like another readout layer, but it's definitely not what Monty is
Right,
made.
that's a good way to put it. So we don't have to give up on that idea completely. But,
yeah, I mean, it could be a flashy demo or something because people are really into generative AI right now. But yeah, it's not really like the.
I think what we have to be careful of is not falling to the trap of trying to do what deep learning models do.
Yeah.
And trying to match them, because probably we won't match them. So, you know, we're not, but I like, you know, the idea that it could be an add-on piece, but I would make it clear that brains and Monty is not a generative system per se, and like certainly for images. And you know, humans aren't good at this. We can't draw things. We actually can't picture things in detail in our heads. So, but as an add-on piece, you know, like, oh, there could be a feeding into another system that does generative modeling. That should be good.
Yeah. I don't think we'll include this part in the paper that we're planning on.
Yeah.
And then, on the second part, the continual learning, I would rename this to unsupervised learning, because we're already doing continual learning all the time, like for point A, for example. This is all continual learning. Like you see the object from one angle and you build a model, and then you see it from another angle and you add points to the model, and you see a new object and you learn about that object without forgetting about that other object. But what we call kind of learning from scratch and the benchmarks, the big thing there compared to the current default setup is that we don't provide any labels to the system. Whoa, balloons.
And we don't make assumptions about the order of the data being presented either.
Yeah, right. Yeah. Yeah, that's something that's different to deep learning. Like we can present the objects in any order. We can learn one object from all angles first, and then the next one, and then the next
Or
one.
you can move your
Intertwine.
finger over an object in one direction and learn a model, and going over another direction and learn a model. It's really a motor-based system. Okay. And is there a reason that A and C are bold?
Yeah, because from these 4 milestones, the way that we went deep into post estimation was we wanted to at least like find a common basis that we can compare Monty against. So that one is order. I mean, we wanted to kind of have a task that people in the deep learning world does understand that Monty can also do. And also I realized that that task is highly related to robust recognition. So that's why it's bolded. So I try to put this in the deep learning, I guess, lingo of current Monty capabilities. So I think what with currently implemented, we can do object recognition and something called 6 degrees of freedom post estimation, and some other future Monty capabilities that may be able to do in the CV lingo is 3D reconstruction. Again,
Just put the word prediction instead of reconstruction.
yeah,
Right.
yeah, and some other possibly like robotic grasping and manipulation, semantic and instant segmentation. But I mean, these are not yet implemented, but I mean, possibly maybe these tasks may be compared against in the future. So because the post estimation subsumes object recognition or often involves object recognition, so a lot of the models, if it's doing post estimation, can already do recognition or sometimes segmentation, kind of depending on how it's implemented. Which is why we focus on kind of, okay, let's dig into existing models for 6 degrees of freedom post estimation. So that's kind of how we went from the milestones into this very specific task. Because otherwise it just looks like we're doing some random literature beyond post estimation.
I think again, what we need to be doing is we need to lay out the basic capabilities of a sensor motor system and then start showing that we're tackling each component of those. And as opposed to being best of class or anything like that. I have a little bit of concern about the robotic grasping and manipulation. That is a very robotics point of view. It seems to me what we really need is essentially a motor output theory for Monty, a more higher level theory about how columns and learning modules can move their sensors in a logical way to achieve goals, and that may or may not be robotic grasping. It could be a lot of things. So we don't want to get down the. I think that would come after we understand a broader theory of motor generation, and we shouldn't focus on that particular type of thing right now.
Yeah, so this is in the future capability. So that those 3, I don't think they will be. I'm very sure that they won't be included in this.
Yeah, I got it. But I'm just saying, even I'm trying to correct potential misthinking about these things right now, right?
Yeah,
so,
but then also like motor behavior will be like one of the prime applications of Monty eventually, I think.
Right, right. So we need to generate a general theory of motor behavior in a sensory motor learning system.
Yeah. And
then we can implement that theory in different ways. One might be a robotic grasping manipulation. But we don't want to go there first. We need this general theory.
Yeah.
Agreed. Right. But for now, the presentation is very highly detailed about the post estimation, kind of went deep.
Yeah, pretty much all the model talk we're actually going to do is going to be about object recognition and post estimation. So I think we're just kind of outlining that.
Yeah. So just
to give a quick more context, I think so. This is not to say, oh, these papers do exactly what we're doing. As far as I
Right.
know, I don't think you found anything that does what we're doing. It's
Yeah.
more like we're going to write a paper. We want to show results from Monty. And it's always good to have something to compare to show how this is really good, because I assume a lot of these systems will need a lot more data or have other drawbacks that Monty does better. So we just want to know what's out there and what can we compare to, at least on some of the dimensions. But
Yeah.
it's not like there will be any like perfect comparison here.
Yeah, I don't think there will be any like perfect comparison at all. And I will kind of go into how post estimation is, there's different ways to tackle it, and how for each of them we can try to relate it back to Monty and how we can compare that to Monty in some similar dimension that Vivian mentioned. So the 6 DOF, or degrees of freedom.
Are we talking about the pose of the object to the sensor? Is that what we're
Yes.
talking? Okay.
Yeah. Yeah,
Or,
so that's,
or just as well as the pose of the sensor to the object. Those are flip sides of the same thing.
yes, yeah. So yeah, so when you just say pose estimation, there's actually kind of two types. Like one is, I think the more common one, honestly, is human pose estimation, because that's very important for, cars not to hit people and whatnot. But another kind of category of pose estimation is object pose recognition, pose estimation, which is generally about estimating these 6 variables: translations along XYZ and rotations along XYZ, with respect to the camera or Monty agent or sensor, whatever you like to call it. So kind of we first dug into, at least I first dug into the data sets, and after talking to Vivian on Monday, I think there are some categories of data sets that we have preferences for. So this is the preference from top to bottom. So we want data sets in order to train Monty or deep learning models, whatever, something that contains 3D meshes, so that it's something that Monty can interact with. That sounds reasonable. The next preferred data set is maybe has point clouds, but not the mesh. In that case, from the point clouds, we may be able to get the mesh, but it's not. It's an additional step. And then the vast majority of data sets that are out there are actually RGB or RGBD images, which is not really compatible with Monty exactly. We'll probably have to do much more pre-processing, like extracting the point cloud from the RGBD, and then from the point cloud, do a surface reconstruction to get the mesh and whatnot. So in this presentation,
in general, Monty could learn from RGBD images, but the thing is, you would need to know the movement between 2 images. So if we would have like the exact pose of the camera when it sees the image, and then another pose of the camera when it sees the object, then we could use that. We wouldn't have active movement that Monty determines, but we could somehow learn from it. And then just to clarify on the preference for 3D meshes, it's not like we're giving the meshes themselves to Monty, but we're using them to render them in an environment which is then sensed by the sensors.
Right.
So for example, we could also just learn in the real world. So we only need meshes when we learn in simulation, because we need something to render it. But we could also just let Monty have an actual sensor and sense actual objects in the world.
So well, the good thing is I think there's still plenty of 3D mesh data sets already that exist. The 3 most common being line mod, YCB video, which is kind of similar. It's not the same as the YCB that we have in Habitat, but a video version, and something called TLESS, which is stands for textualist objects, something like that.
And for whatever reason, YCB video is in a lot of these models.
Yeah.
As opposed to regular YCB. I don't know if that's because they're emphasizing pose tracking as well in a lot of these models, because they're trying to maintain a stable estimation throughout time.
Yeah.
But
yeah, so for a lot of the papers, we didn't actually see benchmark against YCB, but YCB video.
Yeah.
I mean, other common things I've seen was line mod. So these 3, I think, are definitely. I think line mod is the OG kind of the longest existing benchmark data set. And TLESS is often used when there isn't like significant features and So this is a kind of particular use case where, so a textureless would be something like a baking sheet where it's just flat, all gray. So when you move around, there isn't a particular edge that you can extract out from, and those are often for deep learning models harder to do post estimation for.
Why wouldn't there be an edge on a baking sheet? I'm missing that.
I mean, there would be an for the majority of the let's say image of a baking sheet, it's a large pan. Inside the baking sheet is just gray, flat, and it's not really changing.
Right, but if I'm thinking of my fingers running across the baking sheet, when I get to the edge, I feel an edge, right? I mean, that's captured in the 3D mesh, right?
Yeah. It's just
This is more, maybe this is closer to our idea of a morphology class of objects, right? Where you're not paying attention to other features other than just this surface morphology. That would be correct.
To Monty, Monty will be, I think, would do fine on TLS. It's just deep learning models will not do well. Does not typically do well in textureless objects.
Okay.
Could be interesting to test on that and compare.
Yeah, I mean, in some sense, it's getting at one of the core capabilities we think brains are doing. You see, in some modalities, maybe all of them, you're able to detect morphology of objects and features disappear. It's just right. So it just seems like it would be testing that exactly. It's like vision without color and in touch without texture or heat or things like that.
So probably I'm not going to go into all of that, but there's a lot more than these. Some of them I heard are already implemented, like ShapeNet and ModelNet, but from what I see, they don't have, let's see, not this one, but they don't have pose annotation, so I'm not sure how it was used in Monty before, but
they don't need pose annotations. We just initialize them in an environment, like in a 3D rendering engine, and then we can just set how we want to initialize them in this environment.
Yeah. Okay. And so that kind of table kind of summarizing the different data sets to exist. We need to kind of dig into them. So I'll dig into how pose estimation is done. So the good news or bad news, if you want to compare exactly, but I think it's good news. So there's no existing model that I could find or Scott could find that does pose estimation like Monty, which is kind of, I'm thinking about it as like a model or agent that can explore and touch or sense something and try to estimate the pose of it. So even I did find some reinforcement learning based models, but these are still not.
Well, just to be clear, I mean, in the brain and in Monty, you don't really do pose estimation independent of object recognition, right? Those things all happen at the same time. Three things, as you explore, there are three separate things that are resolved. One is, what is the object you're on, where you are on the object, and the pose of the sensor to the object. I just want to be clear
Maybe
that
the scale.
You can't really separate those three out. So when we talk about pose estimation, we have to also, in a Monty setting, we have to also be talking about inferring the object underlying it. You can't do a pose unless you know what the object is and where you're on the object. Does that make sense?
Yeah.
Okay.
So there are several ways that I think also kind of the existing models also does object recognition. So yeah, I think these problems are coupled.
Right, they have to be. I mean, in some sense, there's no way to do pose estimation unless you know what fingers you're looking at, sensing.
Yeah.
So the deep reinforcement learning methods that you found, how are they different? Like, why do they not learn through moving along the object?
So they at least so I found, I'll get to that when I talk about iterative refinement, but they require.
Oh, okay. They don't
Yeah.
use reinforcement learning for the sensing part. They use it
Yeah.
for the inference. Okay, I see.
So yeah, I'll get to that point when I get to iterative refinement. So there's kind of 4 different methods, 4 different ways that pose estimation can be done: direct regression, key point detection, template matching, and iterative refinement. So direct regression is your brute force. You feed in your RGB or RGB data, and you just try to regress, the 6 parameters that define the pose. So this probably this is like the most deep learning brute forcey way of doing it. There's we just let the black box learn just a function from the RGBD to the 6 parameters. How they might be compared to Monty, this is just like a thought, but maybe we could possibly when we're exploring with Monty, we sense color in terms of HSV, and we may be able to extract that and feed that into the deep learning models to train. I'm not sure if deep learning models can even learn rotation and pose at this, like with this kind of small number of patch data that Monty sees, but it's just a way that I thought that could be comparable, trying to put them into the same dimension between Monty and these kinds of models. The key point method is where the deep learning, so instead of directly predicting the pose, it tries to extract interesting points like edges or places where it changes features, and then it tries to match those key points to an existing 3D model, key points in the 3D model. So this one requires a 3D CAD model. And then if you have the 2D key points and the 3D key points match, there are some algorithms, one called prospective endpoint, that you can solve for the pose. So
this seems closer to what we're doing with Monty, is it not? I mean, in some sense, you can imagine, in Monty, you don't sense the whole ducky at the same time. Yeah, you would be moving. You would have to start with one learning module that would move over and detect different points on the object, and through that sequence of points, it would infer the object in pose. So that seems like something what they're doing here. They're creating a series of, I don't know how they do it, but they got a series of points, and then there's that together help them define the pose and the object itself. Is that correct?
yeah, so the features,
Yeah,
I
I
guess I
think
thought
the
that
difference is that this system gets the entire image at once and then uses the whole image to detect those key points, whereas we're getting a small patch that just kind of moves along the object and uses whatever points it sees there. But yeah, it's similar in the sense that we also have kind of 3D models in the background that we match these points that we sense to.
Right. We have a 3D model, and we're taking a series of points until we get enough points to infer the object's pose and ID and where we are in the object.
Yeah.
This is also making me think a lot of SLAM, which is
yes,
slightly different scenario where you're trying to locate yourself, not an object in the world, but
yeah,
they
the
use key
problems-
points a lot in that.
Yeah,
Yeah, but you
So
can use SLAM to map an object as well in the environment, and you can compare that to Monty directly, I think.
SLAM is actually, in concept, a very biologically, it's something brains do. I mean, the details of how to do it might be different, but that's the closest existing research area out there that's close to what I think Monty's doing.
How about training those models? Like, do they just get point clouds or meshes directly, and then, or can you actually get them to learn from observations?
Yeah, I think they use a sensor, like a LiDAR or
LiDAR.
just sensor. Yeah.
For the learning procedure?
Yeah.
Okay.
SLAM is like very related. But anyway, so for the key point detections, I mean, these work pretty well, but they don't, I mean, I think this is probably the most common way that I've seen. But they don't do well in occlusions. Again, if you have occlusions in the image, it can't extract out the key point where the object is hidden. Textureless objects, again, by textureless, it doesn't have interesting features, so we won't have enough key points to match between 2D and 3D and symmetric objects. So for this, we may be able to, I guess one way is that we can maybe just use this as is, but in settings where we have these occlusions or textureless objects or whatever, and kind of show robust recognition compared to kind of existing key point detection methods.
In this case, there's I mean, they process the entire image at once, so how does it do segmentation?
Segmentation.
Yeah, does it first assign these key points to the different objects on the table?
I think it depends on the. So if it's so I think there's some literature that assume or uses only single object on scenes, which is like the simple. In that case, I will do segmentation. I think the others try to do some insect segmentation first. This is just kind of like a general overview, but I think many models do segmentation as part of this key point detection.
Hmm. Well, it's sort of a mystery. You go from this third image to the fourth image, like, okay, how did that happen?
So another third method is template matching, which I thought was kind of similar to Monty's graph matching. This one is where you have some, we definitely need 3D CAD models, but from the models, we try to basically take 2D projections at various angles and try to match the input image to the 2D projections of the 3D. So if I had like a object, then I can take a bunch of pictures at different angles or different poses or different projections or whatever you want to call it. And then try to compare two images. So once there's like a good match, then you would know from which image that it matched, like what the pose was of that object. So I thought this felt like graph matching. But
in the sense that we show the object in a couple of different poses and then we recognize it in any pose, or?
I think in the sense that when we see like a single patch and we later try to like construct the object, we need to match the pose of the object in the memory.
I mean, the object in memory doesn't really have a pose. We just have a hypothesis of how the object we're sensing is rotated, and we use that to rotate our input and then match it to the 3D model that we have in memory.
Yeah. And so in this case, like, it's not that our template is, we have a bunch of instances of template, but I mean, whether we're moving the object inside our head or the input, I mean, for me, I think they're the same things, like which one are you rotating?
Well, it doesn't, yeah, it's not really multiple templates, right?
It's just one 3-dimensional model that we have.
Right. Yeah, so in that sense, we have to avoid thinking along those lines.
But so is this method able to interpolate? So like if the object is in a new pose now that is not in the templates, can it recognize that pose? Or will it just match to the nearest template?
I'm not sure.
Yeah, that's a good question.
Yeah. This to me seems less similar to Monty than the previous key feature method. But
Yeah.
Yeah, well,
Do you know how it's trained?
It's trained on the CAD model plus a bunch of views, right?
yeah. So
So the one nice thing about it, I guess, is that if we wanted to train one of these models, we have, we can generate all those observations from different angles in the habitat, and we have the models.
So in this method, so there is actually a longer training procedure involved. It's not just like you have these 2D views of the object and you're kind of doing like a kernel operation over the image and see if it matches anywhere. Like, do they actually train on like thousands of images before this works, or can this kind of work out of the box with just a few images?
that definitely needs to be trained with many. Like because so again, this one would definitely involve segmentation because the models would kind of exist like without any background or scene. So I think like one of the key aspects of these models is to do segmentation, remove the background, and try to learn to minimize whatever kind of difference function that you set. So for example, the models might not have like the colors on them. So how basically like it will still need to learn to minimize the loss function, whether it's a structure loss or whatever. To say like, oh, this 2D image matches this point of view of a 3D model.
Is this still like a state-of-the-art model?
I think this one, in general, because there can be so much, it takes a long time because there can be so many poses that an object can be in. So I don't think the SOTAs that you found are template matching based, right?
Maybe this multi-view convolutional neural network.
Okay, okay.
But that's also an older one. It's almost 10 years old now, so I don't know if that would be considered state of the art or not.
Probably not. And then the final way to do pose estimation is iterative refinement. So this one kind of starts with the initial hypothesis of what the pose could be. And then, so this one requires an initial pose hypothesis. So that can come from direct regression or any other previous methods, and then try to rotate the target or the object until they match.
yeah, these are all sort of, parallel vision methods here, right?
Yeah.
They're not really sensory motor type of systems, I suppose.
Yeah.
Not money like.
Yeah, there is. I don't think there is a sensory model like that.
Yeah, I know. I mean, well, that's our strength, actually. I mean, okay, let's leave it at that. I'm just trying to remember, are we looking at these different methods for pose estimation as ways we might implement it in Monty, or are we using it ways for testing Monty, or are we using it ways for comparing Monty to other systems?
It's just for the last one. So we're not thinking of using this method, any of these methods to implement in Monty. It's more, we want to show the capabilities of Monty. And to do that, we should compare it to the current state of the art in the field.
Right.
Yeah, I think Monty is already doing better, so we don't need these methods. But we need to find some common ground to kind of compare them, I think. So that's why I was looking into the kind of different methods and what are the common grounds that we can kind of say. Yeah, anyway, so the reinforcement learning methods are under these ones. So this one they kind of pose a problem as navigating through like a hypothesis space. So instead of trying out a bunch of different rotations and trying to randomly match it, the RL method just learns a better action policy to kind of rotate or like kind of move the object in a more sensible, I guess, or in a more computationally efficient manner. So but they're not actually like navigating or sensing by themselves. It's just kind of a method to kind of speed this up, because this is usually the thing after template matching, this is the slowest one, and often post estimation, there's a huge goal to make it fast, aka like real time for autonomous cars. So for those applications, iterative refinement isn't used because it just it improves accuracy, but at a huge computational cost. So that's why some of these like ORL based or other methods exist to make this shorter, because we want to have both real-time tracking and high accuracy. So
Where in this method here, is there a model of the object? I mean, it's not clear. Is it just?
I think they
mean-
just give the raw ground truth CAD models and then put that pose into the renderer.
yeah. So you would have some initial pose for your object, right? So think of that as like a point cloud or mesh that would, let's say like one is flat and there's an object that's like flat on the table, and then we have an object in the CAD model that's upright. Then the object on the table, it will try to kind of move around until it matches the kind of orientation.
So
So I-
the CAD model has a sort of preferred pose, and then it tries.
I think they actually mostly try to find like the relative pose between the CAD model and your existing.
But
like-
yeah, I think I get what you mean with your question, Jeff, because like where's the image going in here? Like the image where we're trying to detect the pose, where does that come from?
So in this case, usually the input is like a point cloud, and that point cloud is coming from pose that was estimated from images.
Oh,
So-
so there's another pre-processing step.
Yeah, because I mean, we need to have some kind of initial guess, so that often involves direct regression. So it often comes from an image. We have some kind of pose estimate, initial pose estimate, and then we can use that pose to convert the 2D to the 3D. And then from there, we try to rotate the 3D object to match the CAD model.
Right, well, this one's a little confusing to me because it just seems like it's, unless it's doing all those CAD models in parallel, like it does them all one at a time.
From the initial, well, I guess there will be an object that was identified. So again,
Oh,
we have to.
so we already know what the object is,
Yeah.
and now. Okay, well, I'm looking at the little flow diagram there, and there's nothing in the flow diagram that explains what the model of the object is. It just says, initial
Yeah.
pose, change the pose, initial. It's like, well, pose of what, I don't need to get into the details unless it's something we're gonna really rely on.
Yeah, but I think this one probably is at least. Yeah.
So I have a question. I'm sorry, my Zoom was cutting in and out, so I missed part of the discussion. But did you cover ransack methods for pose estimation?
Yes, I mean, I didn't say it here, but during perspective and points, it's often coupled with ransack to generate possible pose hypotheses.
Okay.
Yeah.
That I hadn't seen that one particular image where they were kind of going from features to pose. Got it.
Yeah. Sorry, I mean, I guess I copied these diagrams from a review paper and that's clearly not good.
Okay, thank you.
Yeah, but yeah.
So which of these methods would you say is the best state of the art at the moment?
For me, it's key point. I think that's
Okay.
yeah.
And so you said there was nothing out there that uses the same kind of inference regime where you have a sensor that moves over the object, right?
Yeah.
You know,
Okay.
let me ask a sort of a higher level question. So in Monty, in the brain, we have learning modules. Each learning module, of course, can do this independently of all the other learning modules. But of course, they also vote on this as well. So that's why we were able to do flash inference. Are we going to try to demonstrate both of those initially, or are we going to just try to show how a single learning module does this?
Both. So the voting is, I think it was 0.2 of the capabilities that we want to demonstrate.
Yeah.
If I remember. Yeah, rapid inference with multiple sensors.
Okay, so that multiple sensors includes multiple vision patches or multiple
Yeah,
somatic
exactly.
sensors. That's even I got fooled by that, because maybe if it said multiple sensor patches, that would be clearer. I took that to mean, and I think most people take that to mean like, oh, vision and touch or vision and hearing or something
Oh,
like
that would be the multimodal transfer, I guess.
Okay, well, maybe we could just change B to say multiple sensor
Yeah.
patches.
Yeah, I think I also confused that, Jack, when I was first going
Yeah,
through.
yeah. I mean, you know, it's a general rule here.
Yeah.
Monty works very differently than almost every other kind of learning system out there. And we need to be demonstrating that we're making progress on those components of how Monty works. And that's more important than showing that Monty is better at other systems. That's a losing game initially. We don't want to go there. We really want to say, hey, it's some unique capabilities. We're starting to show how they work. It's almost like illustrating and teaching people how these systems, how Monty and the brain actually do these things, which is more important than actually saying, oh, we beat, you know, we're better at this benchmark than these people are. So I just want to make clear that to me, it'd be more important to say, oh, well, let's talk about how a single learning module does this. Let's talk about how they vote to reach a consensus more quickly, and demonstrate that we can do that. I'm not against comparing it to other systems, but we have to be really careful. If you compare to other systems, you're not better, than the machine learning world will just ignore you. They don't really care how you do it. They'll just say, well, on that benchmark, you're not as good, or you're about par, so who cares, type of thing. You know what I'm saying? We don't want to give people that view. We want them to say, hey, this thing works differently, and look how cool it is that it works, that kind of thing.
Yeah, I mean, but one, I think we would beat all of these approaches if we make it with the same amount of training data. Like they get as much training data as Monty gets, they would probably all fail completely. But now seeing that you didn't find anything that even works closely to how Monty does inference, I wonder if it would make more sense for us to just put out new benchmarks. We could ourselves try to train a reinforcement learning agent on it, or something that we think would be best, a transformer model or something, but then just kind of put it out there, say, humans can do this. Our system is very good at it. Try to solve it in a better way, kind of thing.
Yeah.
Well, you could do that in the form of a demo.
Yeah.
Well, I mean, I don't know. I mean,
Because that gets people intrigued with, you know, how are you able to accomplish it, rather than trying to go against oh, here's a 1,000 object library, and you know, here's how we stack up against something else. But if the demo illustrates unique features of Monty, that might serve as a teaser for people to get more interested.
Yeah. Yeah, and I mean, the demo could be something like a benchmark as well, not in the sense as like, I mean, it could still be something cool, but in the sense that like try to solve this task in a better way than we do.
yeah, I wouldn't want to make that challenge. I think what we would want to do is we want to show how the system works first. That is the most important thing. How does this system work? Single learning module can do it through inference over time, movement. Multiple learning modules can vote to do this more rapidly, and then characterize that. Like maybe we do some sort of capacity testing, or you know, performance testing on just for ourselves, for starters, you know. And then after you've done all that, you could then compare it to other systems. But But really the goal here is not to get people to say, oh, this is better than system X. The goal here is to educate people that there's a whole different way of doing these things. And I think in some sense, we're going to have fans who just have bought into the whole thousand brains theory. And those are our audience here. The audience of people who basically think like deep learning can do everything. Our goal isn't to try to convince them at this point. We have to stay away from that, I think. So as long as we focus on, hey, this is how Monty does it. These are the capabilities of it. Its limits and potential. Oh, by the way, if we can say, it's better than other systems, but that can't be the main focus. Because then someone will come along and try to do something different with another system. I don't know. We don't want to get stuck in this benchmark hell.
And we also probably need some brainstorming session to kind of creatively show Monty, or maybe not even creatively, but show Monty capabilities, and not just focus it on how it performs, but how it's a different paradigm for doing it. But so like, yeah.
Right. I mean, that is, it'll be a while before Monty is beating other systems at various benchmarks. Maybe I'm being too pessimistic on that, but I view that as not our goal. Our goal is to really just continually talk about, this is the way the brain does it. This is a different way of doing it. This is one that's built on movement and sensation, and that's unique. And here are the components, and we're making good progress on them. And if we can then say, oh, by the way, it's performing state of the art, that's okay, but we don't want that to be the main goal.
Yeah,
So I would
here's
characterize
how
that as focusing on qualitative differences rather than quantitative differences.
Right.
Yeah, I mean, here's how I'm kind of thinking of it. So we already have a lot of written up on how the system works, what the principles are, how we do these things. And I was planning to turn all of that into a white paper that we are already going to put on arXiv pretty soon. So like once the project is open source, people can really read about how does it work. But people will ask, what can it actually do? In what cases would I want to use this system? What are the capabilities? And there we want to show like, okay, it can learn from very little data. So if you have an application where you don't have internet scale data sets, you might want to consider this.
All right, I agree with that. That's the right approach. It's more like the unique capabilities and where might that be useful, as opposed to comparing to other systems that, some sort of performance benchmark, what I'm saying? You just got to be careful about that.
And yeah, we don't need to compare to a bunch of other approaches. This is just an initial literature review to see what is out there. Are there similar approaches that we should look at? It doesn't look like there is an approach that uses the same kind of data to infer from, so it might be difficult to even do a fair comparison. But yeah, it would be nice to at least kind of have a show where we take the exact same data that we give to Monty, and then we give it to a transformer or a reinforcement learning agent, and it just kind of fails because it's not enough data, for example.
That would be nice. It'd be nice to do that.
Yeah.
But I don't think it's an absolute requirement. So if we can do it, that'd be great.
Sounds good.
Yeah, I think it's gonna be hard to find a one-to-one comparison. Like, let's say we even trained a transformer with the data we collected from Habitat or something, or 77 objects. We'd still need to feed that transformer a whole image, like what a viewfinder gets, unless we want, because there's no like architectures that we know of that are going to take image patches and try to detect an object from image patches. So
we could give it a series of image patches plus the movement or the change in location and orientation over time.
For transformers, I was thinking like patch views, like the small patches that it takes for Monty to get to recognize. So if it takes like 1,000 steps, then it'll be 1,000 patches. And the positional embedding can be like the difference in location. But I mean, it is.
But then we're designing our own transformer network to do this, right? Like those aren't pre-existing
Yeah,
state-of-the-art models, like if I understand it, why,
yeah.
I'm not saying let's not do it or whatever, but like to my knowledge, there aren't any pre-built systems out there that are gonna work on these patches.
Yeah, there's no,
Well,
yeah,
if you look at vision transformers, they actually break the image up into patches just as part of the training with encoding of relative position. So it's not totally divorced from what you're talking about.
Yeah.
yeah.
Okay, so
But
we
they
would
just
just need to
they
figure out
just-
how to
They
get
just
our patches.
serialize an image, right? It-
Oh, they actually break it on up into each patch is an input that is encoded. It's in a way you could think of it serialized, but they try
Yeah.
to keep some of the two-dimensional aspect of it.
Yeah, I've read
So
about this.
so the transformer doesn't have to learn the whole serial to 2D transformation.
Right.
Huh.
It's using the word patches, but it's somewhat different.
Well, it's a subdivided image, so it's not they're not free floating patches, at least the way it's conventionally trained. Doesn't mean to say that you couldn't try to do something like that. So I'm just trying to sit some space in between. We're looking at totally transformers, and we're trying to look at Monty. Vision transformers have an intermediate aspect to it, which is not totally divorced from breaking the image up into patches.
Yeah.
Could you, in theory, then just like, let's say you wanted to just simulate having looked at 3 image patches, can you just mask out?
Yeah.
Well, I think basically they tend to subdivide the image, but I don't think there's any reason, as long as you have some encoding of the relative relationships between them, of having patches that overlap or in some other aspect. So you could gradually move from a fully, rectilinear Cartesian orientation for the patches, maybe to things that were starting to get looser. But at this point, I'm speculating because I can't point to a paper where they actually did that. I'm just saying there's the thing about vision systems, whether it was convolutional neural networks or vision transformers, was that there was a huge amount of redundancy because there's this 2D, things move slowly across the image, type of thing, as opposed to linguistically. Where things are not nearly so coherent. And within the space of that, if those things work, you start kicking the system and relaxing some of the hard constraints and see how well it does. But like I said, I'm just saying there is a framework there. If for whatever reasons you wanted to draw an analogy or comparison, there's a starting point.
Okay, it's good to know.
Yeah, that could be worth looking into a bit more. I feel like that's almost the best way for us to go, to keep the exact same training regime we have for Monty, and then try our very best to train a transformer model or a deep reinforcement learning agent on that same data.
Yeah,
I wouldn't want to spend a lot of time on that. That could take forever, maybe.
I don't think it would.
Okay.
Yeah.
Hey, can I ask a slightly different question? In Monty today, I should know this, but I don't. Do we vote on pose already across multiple learning modules?
Not really. So we take the relative pose of the 2 sensors that are voting into account, but they are not communicating their hypotheses of the object pose to each other.
Is that something we should be working on?
Yeah, it's on the to-do list. On the
Soon?
very long to-do list.
One of the things that occurred to me is, we want to highlight capabilities that are unique to the system, regardless of how they compare to other systems. And, we think about almost everyone thinks about vision as this image. And then there's these patches on the retina next to each other. But we're not limited to that at all. I've said this in the past. You could have an image system where you've got 3 cameras in different corners of the room. and each one is attending to some patch in its visual space. And as long as they're all looking at the same object from different directions, it'll all work just fine. It's sort of like people just don't think along those lines. And so one of the things, it'd be nice to demonstrate what, sort of like having two fingers touching the object at different locations. It'd be nice to somehow, if they were, illustrate the benefits of that. It's a system that can handle these sensors that are in different locations and unite them in a single, very rapid way.
Yeah, that reminds me, are there any approaches that do object pose recognition from touch sensors?
I didn't see anything like that.
Yeah.
Okay,
So I can go back
might
and
be-
sort of refine the search with that
Yeah.
particular modality in mind, because I'm not surprised that it wouldn't have come up, given the way I was searching, if that does exist. But just
Yeah,
LiDAR, I don't know if you.
In the neuroscience world, they almost completely ignore somatosensory sensation because they have no idea how to handle it. The classic, a hierarchy of feature detectors model doesn't make any sense with fingers and skin. just people have avoided it. They're like, on the neuroscience side, I'm not aware of any theories that explain how we recognize things through touch. Just point that out. So I wouldn't be surprised if there were fewer in the machine learning world as well. Because people, it just doesn't, people can all say, oh, it's an image or these patches. I'm looking at the object, where when you have fingers touching an object at different places and locations, what the hell is it? What's going on? They don't know what to make. They have no idea what to make of that.
Yeah, I'm sure there's a lot less, or if any, machine learning research on that as well,
Right.
like pose recognition from touch. But I wonder if it might actually be good for us to phrase it as like recognizing the object through touch, because exactly like you say, people are, if you think about vision, they're used to thinking about the entire image, and for them to understand that those are a bunch of small sensors moving across the image, it's going to be hard to, like, a lot of people, we might lose a lot of people there. Whereas when we say, okay, we have 3 fingers that are moving on the object,
Right.
that might be easier to understand. Why do I keep getting balloons?
It's weird because, I mean, this has really messed up all kinds of AI and machine learning and neurosciences all these years. The real breakthrough is understanding, patches of the retina are really no different than patches of your skin. And it's something that most people just don't understand. So our job is to educate them.
For touch data, what the closest thing, what would a touch data, like, I guess one question, what does touch data look like? And maybe the closest thing I can think of is depth, because you can think of depth as how much I need to move my finger to get to that object. And if I phrase the question as, is there any models that does pose estimation from depth? Not just from depth, it usually involves RGB as well. That's sadly, that I don't think I've seen a model that just on depth, but those might exist, I guess.
Yeah, but then they get the entire image probably, and not just
Yes.
the small
Right,
patch
right.
that moves over the object.
Yes.
And I don't know if there's research, but in like autonomous driving space, a lot of the new LiDAR sensors are not scanning, they're just fixed orientation. So they're looking out from the car with a specific focus and are going to move with the car. So maybe there's something there.
Is that right?
Yeah, I mean, definitely like the Google cars are still using fully scanning LiDARs, but it's a much more expensive device. And so there's a whole slew of companies producing essentially LiDAR cameras, if you will.
Okay. Interesting.
They still scan the laser within a defined window.
Okay, so they still scan, but they don't rotate.
Exactly.
Well, that's just it's a matter of degree, I suppose, right? They're sort of doing
I'm just thinking of a place where someone's, getting sort of a small patch of LiDAR
Yeah.
information.
Yeah. They probably build up a 3-dimensional image from that, and then they process that.
Yeah,
Yeah,
I don't
right,
know how they're doing it.
right.
All right.
Did you
What
have
about
any
models?
other approaches to talk through, or?
I mean, so those are the like 4 major categories of how pose estimation is done. I think the rest of the slides are kind of SOTA models. Yeah,
So yeah, I
and some
guess,
metrics of how pose estimation is, how their performance is measured. Because I guess if we were to go this route where we're comparing to deep learning models, then we probably want to compare against, use the same metric to compare. So, but I mean, it's not I guess it's not the highest priority now, but yeah. But
I mean, the rest is like just a collection of what we assembled as like most promising. If we want to go down this route of training a model on Monty type data for comparison purposes, these are some promising options for object recognition and pose estimation. They work in slightly different ways, and in order to know like how much of a haul it would be to get Monty data into a format that is compatible will still take a little bit of work. I need to download some training data and see what format it's in. Some are pretty interesting. Foundation pose is probably it's up there as state of the art. That just came out this year. It's got 2 sort of modes of training. You can give it those CAD images or CAD files, or you can give it, images from different angles. And that's sort of its model-free training mode. And from that, it kind of works on like, it develops category ideas. So when it can encounter novel objects and estimate their pose by associating with some kind of similar object or category of object. It takes a ton of training. So,
is that for the model free or also for the model based version?
both.
Okay.
The model free version, to my understanding, it's sort of a pre-processing step. It's going to get you to something like what a CAD file will get you by giving, it'll basically reconstruct this mesh. So it's more of a pre-processing step, I guess. But
Yeah, it seems almost like it would be fairer to compare it to the model based approach. Kind of saying the CAD models are a bit like our 3D graph models. We disregard that the training is different and that they just get them. And then, I don't know, I'd be curious about how they then, like what kind of data do they then use for inference? And how do they process it and recognize the pose?
just I think it takes single RGBD images for inference. It's pretty fast. You can do it in real time. Like you can click on these links and get the demonstrations or whatever. I mean, I wouldn't call it continual learning. It's not going to keep adding to its database of objects, but it does at least have the ability to estimate pose of novel objects just by associating with the category. So it's like a little less brittle than something that's, it's not continual learning, but at least it doesn't freak out when it sees something brand new.
Can you open up the paper and just kind of show the figures in there?
there's so many
Yeah.
things
Oh, they
going on.
use language too. Okay.
Yeah.
The Objaverse. Is that a universe of objects?
Good question.
Okay, this looks a bit too complex to understand with a quick look. But
So
yeah,
I mean, I think for like this kind of comparison, seems like where we're going is if we want to, again, low priority, I agree that we can use transformer to like feed in patches, but it will be patches that Monty sees that we feed in. Like I don't think we can like train these models with 1 million images, nor
Yeah.
I don't think we want to, or I don't want to personally. I'm not trying to recreate a sort of deep learning like thing, but it's so I think what we can do is we can like start from like a basic vision transformer. We can possibly add some bells and whistles from SOTA, like some of the techniques. But ultimately we'll probably be training our own kind of custom transformer that sees the same things as Monty, let's say for patches. And that would be kind of a comparison to Monty.
It strikes me a little odd that we would take Monty's training data, which is a series of patches and movement information, and then try to train a transformer model on that. It's like, I'm trying to put my finger on what's odd about it. Again, I'm just going to repeat what I said earlier. Our goal isn't to say, oh, our algorithm at doing this is better than. It's more like our algorithm works differently, and these systems don't work this way. And, I mean, because we train a transformer on a series of image patches that Monty gets, it'd be hard to argue that that's a fair comparison, for the benefits of doing it Monty's way, People might dismiss it as like, oh, you trained this thing, it's weird data, why would you do that? I don't trust that you trained it properly, that kind of thing.
And there's that kind of disconnect. Like, yeah, for all these things, just because of the way the Monty collects observations and does inference, like the actual training process, the inference process, what the information is for these different types of models versus what information Monty sees, it just makes it very difficult to like try to do a one-to-one comparison, I think, with any of these other models.
I think possibly what could be getting similar is using insert transformer, possibly like RNN. So for every step patch that it processes, it might have a pose, and the more patches it sees, it can try to refine that pose. Maybe that's closer. But again, I mean, I think that one at least takes into account of kind of sequential kind of processing, perhaps. But yeah, but I mean, otherwise it's just, I mean, it's probably nonsensical to like download these foundation models with the 1 million or images and try to train that and compare that to Monty. Like there's no point of doing that.
Right.
Agreed.
yeah. Yeah, it looked like they tested on YCB. Can you go show what the results were there?
Okay.
YCB video, I believe.
Yeah.
Oh, okay.
But it does have a potted meat can.
Yeah. And since some of the objects in YCB, I mean, I think 21 of the objects from YCB were made into YCB video, I think.
Okay.
Yeah.
So these all sound familiar. The MasterChef can. Seen that one many times. The mug and the bowl. Okay. And then those numbers are accuracy on pose detection.
This stands for average distance. So after getting the pose, they make it into 3D, and so they calculate. And then after the 3D model, they compare that. So compare that with a ground truth pose rendered 3D, and then calculate the Euclidean distance between every point, and then average that.
So bigger is better?
No, smaller.
I would have thought with distance that smaller would be better, but here they
Yes.
both the largest values. I guess it's like 96% correct or something like that, it means, maybe.
Possibly. I know that's confusing. So I did like.
Okay, it's not that important, but
Sorry, I did write like a metrics section, but it doesn't help. Okay, never mind.
By the way, if you are interested in any of these papers, there is a folder where we've dumped a bunch of these papers into on the Google Drive.
Cool. Yeah, so I wonder if it makes most sense right now. We just focus on creating plots that show Monty's capabilities. So how we are good at all those things, learning from little data and so on. And then we kind of mention all of these approaches, say, okay, this transfer-based method uses 1 million of images, instead of actually trying to retrain it on exact Monty data and trying to compare it.
I'm not in the
Yeah.
machine learning world enough to know whether or not this would be fair or not, but to actually just side by side show how much actual information is being provided to the system before it comes up with a positive result, like something like that, comparing that with other models. I mean, instead, beyond just the training data, because if we are just using patches, you know, that could ultimately be a lot more parsimonious of a or we can show efficiency basically on inference if we're talking about sensor patches versus whole images,
Yeah.
possibly.
Yeah, we could have one of those log scale plots with number of images seen and then this at the bottom and transformers are all the way up there. But yeah, I guess the problem is that the performance measure is also different and we get patches and movement data and they get full images. How do you compare those numbers to each other?
I mean, I think if the reader is like a kind of actually now, if they're truly concerned about Monty performance, and they can like just read these papers and kind of see like how people are doing in these YCB video data sets, like right, like because the way that we're doing is so different that it's basically incomparable for the most part.
Yeah.
Well, you have the input data side, but you also have, I mean, the intrinsic number of parameters it takes Monty to, once it's trained, to represent things compared to, some morally equivalent transformer out there. I mean, I'm sure you'll win on the parameter side of things.
True. Yeah, that's another comparison we can make.
But I think I agree with what you said earlier, Vivian, about kind of focusing on visualization or plotting to show Monty capabilities.
Yeah, and then we can just kind of do more of a literature review of the other approaches and highlight how they are so very different from what we are doing, and then maybe have like a plot or table comparing number of examples seen and number of parameters internally.
Yeah, I guess it could go into some like if we're writing a full paper, like a background and kind of what's been done previously. And that would be much easier to like pull together the table of number of images and kind of how it's doing than trying to like test a bunch of these models for sure.
Right, I agree with that.
Also,
We just don't want to do that.
Because yeah, we kind of already know, and I think every machine learning reader would know that if we would train a transformer on the amount of data that Monty is trained on, it would just fail. So
like we don't need to train a model that would fail.
Right.
yeah.
If you need someone to train a model to fail, I'm your man.
Get an undergrad, get an intern. Okay. Yeah, I guess that's about it on our side, I think.
Yeah, it was helpful, useful just to see what the state of the art is out there. And it was also good to have this discussion about what we're trying to do.
Yeah.
What we need to do.
Yeah, thanks for putting together those slides.
Yeah. It's very interesting.
And now you know a lot more about object pose estimation, probably more than you care.
Well, I wasn't even aware of any of the state of the art out there. So for me, it's a good introduction.
I dropped the salient image of vision transformers into the chat. It just came from the Wikimedia Wikipedia section on just input vision transformers, just to show that that parsing that goes on.
Cool,
Sorry, I can't
thanks.
like move the chat to the screen, sorry.
Right.
So you'll just have to open the chat yourself and kind of see, but
Okay.
Okay, so yeah, I guess we took the whole meeting, but I think this was a good discussion. And then, yeah, for next week we can go over all the other smaller topics, and I'll have a bit more time to prepare answers. And I think Jeff, you offered also to give some answers to some of the questions, like the
Yeah,
grid.
right. Remind me again, like on Monday or something.
Right, will do. And yeah, if anyone else wants to send in some more questions and topics you'd like to talk about, just post it in the research channel.